Okay, starting.
Okay. Yeah, I'd like to thank the organizers for the invitation. This is a beautiful place, like in America, so I've never been. So it's kind of an experience in itself, and also a kind of nice set of people like just with. So today I'm going to talk about how to go from classical scattering amplitudes to bound-state observables, so the in the post-Minkowskian framework. And this is based on some work I've been doing with a few collaborators. Not all of them are listed here, but these are the main work I'll talk about. So one is Xin in Beijing, and the other two are Tim Adamo and Anthony Delto at the University of Edinburgh. So, okay, I'll start with some motivation introduction. Why I want to look at scattering amplitudes, why they are, I think they're important for these gravitational wave searches. Then I will try to develop some relation between amplitude and actions from the classical GR perspective, and how this can help us to understand like relation between bound and scattering orbits. Because what we're going to talk about is scattering orbits mainly, but there is a map, and that's the main focus of this talk, between the scattering and bound case. Okay, then I will focus on a particular case, which is the boundary to bind dictionary for generic orbits. We know the probability is very important. It's the building block, for example, in the cell process function is one of the cases which you understand very well. And I would like to fully uncover the structure of the this boundary to bound map for generic orbits. And then we will look at observables, how to grab observables from this structure. And finally, I will briefly talk about some extension of this beyond the problem like for active observables, although it is very much work in progress. All right, so I would say that as we learn, like in these weeks, like the discovery of gravitational wave really calls for new analytical tools and to study the Chukotay program. And in particular, we need to wait for templates and for the mass filtering, as many of the data analysts have explained in these days. And the goal here is to learn like some piece of the waveform, some data of the waveform in the first, in the spiral phase from effective tools, which allow to study like these compact objects as point particles at large distances, which interact through gravity. And in particular, like we want to learn some analytical results for this. Okay, so there are a lot of numerical tools like numerical relativity and many others, but like I would say that it's important to understand like the space of functions, and in the result, it's important to understand the analytical structure. So this is one of the main goals, like trying to understand this analytical structure of the two-body problem, at least for this spiral phase. And the main idea is laid out in this nice work by Goldberg and Rothstein that was also mentioned by Riccardo, where point particles can be taught as, compact objects can be taught as point particles at large distances. Okay, so since the program is about scattering amplitudes meeting gravitational waves, I thought I was just making a small cartoon. So here you see a 5-point amplitude with shaking hands like with the waveform templates that actually Patricia showed us last week. And one of the questions is, you know, we want them to meet, but why amplitudes? So I was just going to provide some introduction to what, roughly speaking, amplitudes are. So there are some gauge invariant objects, universal objects, which encode like the perturbative scattering between two bodies treated as point particle. And the interesting part is that this can be computed in analytical form. And on top of that, they offer a new perspective on general relativity. One of the things I've learned from this program, like of trying to develop scattering amplitudes for gravitational waves, is, for example, how to reconstruct the Schwarzschild method from these objects. So how to reconstruct the stress tensor like of Schwarzschild, like directly from this type of amplitude. So this can be done, and it shows like that really you can match one by one, like what people in general relativity can do and what people in amplitudes can do. Of course, it requires some resolution, but yeah, let's talk about it separately. So yeah, that offers a new perspective on general relativity, and we would like to kind of see the two things taught together. All right, so we would like to understand like classical bound states again, right? So and these are related to scattering amplitudes, as we'll try to explain. And usually when you have a difficult question, you look at some quantity theory textbooks by Weinberg, for example. But there is this message that he wrote down in text, like it must be said that theory relativistic effects, relative correction both states is not entirely in a satisfactory shape. So I like this quote because it seems like, you know, it's not that it's not straightforward like to mount like scattering and bound matrix elements, but there is some hope, and we hope to make some little progress over what was not known at the time when the quantum theory text was written. Okay, so yeah, one possible answer to this, it's not unique, but that's the one I've used in this talk mainly, is the amplitude relation, which I will discuss. Another question is, can we push our analytical tools like to really, you know, how far can we go for bound orbits, like starting with scattering? So of course, scattering orbits like are really a large simplicity, so large angular momentum, orbital angular momentum, and we want somehow like to at the end get some results which is valid for more circular type orbits. At the moment, we know that most of the type of orbits for the current gravitational wave templates are basically circular orbits. So we won't like to get to that at some point. So it's important to see how far we can push these analytical tools to understand at least the functional structure, as I was saying. Yeah, and one possible answer here again, like only one of them, is the bound dictionary, which I will explain. I also think that one important question is, you know, how the resummation enters. As I was saying, like for example, if you try to reconstruct the Schwarzschild metric by a massive point part contracted with gravitons, like you need to resum all the orders if you want to really construct the full metric. So there is a resummation involved, and these resummation are playing always a very important role in the current analysis. And even the plots like that people are making, like using the Hamiltonians, for example, provide like this post-Minkowskian methods, they're all made by resumming some particular contribution. For example, the field source estimation, things like that. So I think it's very important in the Salzburg place the estimation in G, but it's an expansion mass ratio. In any case, I think the estimation is a very important tool, and in the ideal world, we would like to put all our data to some model like the fatigue one-body method, and then use that to compute the waveform templates. All right, so I will start with something very, very simple. So how can we describe bound states of point particles? And one really naive thing is start with the relativistic hydrogen atom. So everyone here, I think, knows how to solve it. We can solve it for both positive and negative energies. So this is an interesting playground. Like, so you can have like a continuous spectrum, some confident hypergeometric function we describe the scattering of you know, this point particle in this potential, one over potential, or you can have also some normalizable wave function, something like Laguerre polynomials, so things like that to describe your bound state. So we want somehow to connect these two things in some kind of limit, which is related to the classical limits. And the interesting thing is also here the spectrum is continuous, spectrum is discrete. So in some sense, we want a limit of large quantum numbers, this classical limit. So that's how you make the correspondence. Yeah, using perturbation theory, this requires like an infinite sum of this potential. If you compute as we will do in post-Minkowskian, like in perturbation theory, you have contribution from this first order iteration and the second order iteration, and you have to reassemble them to get the exact answer, okay? And this is, so in some sense, bound states are intrinsically unperturbative, requires some resummation. You cannot see, as I will discuss, like bound state poles, for example, in the S matrix, unless you really resum things.
Normally, what you do is that even if you make the sum, you don't get the result, like an explanation.
Yeah. No, I mean, I just, well, what I mean is that people always talk about destruction poles and their relation with the bound states, that these only arise from our estimation. That's what I'm saying here. So that's what I'm going to try to describe. Right, so the generalization of the previous picture. So if before we had a potential, the potential can be generated by another body. So if you make it generated by another body, you get what is called the ladder approximation. So that's an easy way to see how diagrams start to come in, like in this picture. And this is actually used for QD bound state for positronic. This is a non-relativistic picture because that's basically it doesn't include this cross ladder exchanges in which need to be included when you go to relativistic physics. And we can write these things in an interesting way, which is a recursion relation for amplitudes, which is called like Benz-Peter equation. Or if you want, it's just some Swinger Dyson equation for your 4-point function, which you just put on shell and you write out the recursion. And if your kernel is the 3-ladder exchange, then you just reproduce this ladder by some iteration. So in some sense, we want to resum those objects and also try to make contact with classical physics. Okay, so that's the goal for today. All right, so this Benz-Peter equation, like, was interesting. It was found by two physicists. One of them is an astrophysics, which is Salpeter. That's actually work on the mass function for the kind of the probability distribution of masses in a star formation. And Hans-Peter is a nuclear physicist, so I thought it was funny that since we're trying to meet amplitudes and gravitational waves, like these two actually work on exactly the same, different kind of models. And the equation basically is just this iteration of the 4-point amplitude, which is these objects that this equation described here on the right, which basically says that your 4-point amplitude of the interaction is given by some iteration of the kernel with a two-body propagator. Okay. And the question is, how can we take the classical limit of this? This is a non-perturbative equation. I said it's if you like this whole Swinger Dyson equation, you get land exactly on the same things. If you work on, I was going to stress this, these are for two massive particle irreducible diagrams. So you need that, like, if you cut into two, like it cannot be cut into two. The small pieces of the diagram centering the kernel, they have to be two massive particle irreducible. We will get an example later, so that will be clear. Okay, so as I said, the frame we will use is quantum field theory, point particle interacting with gravity. It could be spinless, it could be spinning. The framework is very flexible in general, and if you want like some extra effects like tidal deformation, you're just going to add higher dimensional operators essentially. But I won't talk about it today. So what you can do is essentially what you want is the exchanges to be very soft. So you want this body to be very separated within effective field theory. And therefore you want your momentum transfer to scale essentially like h bar. And this is achieved with the following parameterization, the stellar momenta. So this is a kind of nice trick to already see like which kind of diagrams can appear in the classical limit. And as I said, it's related to this, like point particles interacting large distances. So they exchange some momentum transfer, and that has to be very soft because the wavelength has to be very long. So that's the kind of idea in the effective theory framework. All right. Any questions so far? Okay. All right. So we can just quotient. So now what you want to do is essentially see how the previous iteration that I was describing here gets modified, like once you post this constraint of software changes. Okay. So this must slightly change the equation. Right. I have a question. What is K? K is the kernel, is made of two massive particles with 4 diagrams. So it's all the diagrams like this. So as was the example before, something like this that cannot be cut into two. So that's the kernel, for example. Yeah. So the ladder will arise from iteration of this two massive particles with 4 diagrams, which just arise from iteration. Okay. Yeah. We just want to solve this non-perturbative. We'll make contact with the explicit results later. All right. So yeah, we want to implement these soft changes, this kind of scaling. So what you want to do is essentially symmetrize our internal gravitational exchanges. So if you think that your exchange is mediated by a classical field, you should not be able to distinguish any type of gravitational exchange with each other. So if you have a box diagram, this diagram, this diagram, and this diagram, you have to sum over, because you cannot distinguish like the two gravitons from each other. So this is the physical principle. So you want the wave to be independent of the single graviton property. So you want to basically get rid of that. And the way you do it is you symmetrize over internal graviton exchange.
These are not supposed to be part of the kernel.
Sorry?
These are two particle reducible, right? So
That's right. Yeah. This is it. But I'm talking about the second part of the equation, right? Yeah. Indeed, like the first part survive. So yeah. So indeed, like the first part for equation survive. So that's the one made of one particle reducible diagrams, and the part made of higher order reducible diagrams just arise from iteration. The interesting part is that the two-body propagator that was there before gets replaced by the Onshore version. Some might be familiar with this, like it arises everywhere, like in borderline quantity theory, or like if you do any kind of things that is semi-classical, essentially you always get a delta function imposing, if you want, energy conservation. So it's just for the two particles over here. So you get an equation of this type, which now you want to solve and make contact, for example, with the Kona exponentiation or things like that. I will describe in a second. Okay, so the interesting part now, as you can see from this equation, the pointer, okay, this is a convolution, okay? So we know convolutions are diagonalized if you go to the conjugate space, in Fourier space, so convolution become products. Because of this delta function, you get rid of two integration, then you end up with a convolution in two-dimensional space, and that convolution will get diagonalized when you go to hyperparameter space. So you want a Fourier transform essentially in this exchange momenta, okay? And the idea here is also, I will say later more about this because it's very interesting from a perspective. So yeah, as I said, you do Fourier transform in hyperparameter space, and what you get is just that what before was a convolution becomes a product. Sorry, the laser is not working well. Okay, in the second line, what was the convolution becomes a product, and because it's a product, we now iterate this and solve it, and the solution is an exponential. So this is explaining why the solution is an exponential, if you want, like it is related to the standard Icona exponentiation, but I just want to show that here it's really starting from the single Dyson equation. So you just impose a physical principle, soft exchanges, you impose this physical principle, you end up with the result answer. And this is what it should be. So classical physics is like saddle point in the action when you have an integral, so it's going to be exponential. If you want to just find another way, but making use of amplitudes. There is a generation for spinning particles, but I don't have time to talk about. So of course, in that case, there will be some non-commuting vertices on each line. So you have to care about commutators of spin operators, but they are suppressed at least a leading order. And it is believed that there should be some kind of exponentiation for some kind of spin. Okay, I want to talk about this today, not too much at least.
So what does it mean going to impact parameter space and boundary?
Exactly. So this is very interesting. So the thing is that you want. So when you solve, so let's come back to the previous hydrogen atom picture. So if you consider the solution, of the Hamiltonian. So what's the solution Hamiltonian in the scattering case? In the scattering case, it's going to be a sum over partial waves. So it's infinity, and then you have some psi of L essentially that you have to sum over. But if this is for scattering, right? So for scattering solution, you're always going to get a sum of partial waves. In the bound, if you consider any bound solution, is labeled by the quantum number. So the bound solution will just be psi L. So what you are doing secretly, you want to make manifest dependence of orbital angular momentum. By doing that Fourier transform is going into partial wave basis, essentially. So that type of parameter space has the meaning of going to partial wave basis. And the reason is because in partial wave basis, the solution is bound. So if you want to get a bound solution, you always want to work in partial wave basis. It is the critical point behind it. So if you want to go, this is the reason why you want to trade your transfer momenta with the hyperparameter, and then which is related to the orbital angular momentum. So it's a very trivial thing, but in some sense, it's just a carryovers in a quantum theory perspective. So yeah, so we're trying to go to partial wave basis, essentially, if you prefer. And yeah, so here there is an interesting observation. I'm not going to have time to discuss, so I'm going to discuss afterwards. So we did some analysis of these integrations. So you might ask, okay, now I have my something, and if you know the kernel, as I will discuss, we know this kind of iconal phase or kernel, you can ask what is the pole structure of the amplitude. And people can do analytic aesthetics bootstrap and things like that care about exactly this structure. So it turns out you can carry out these integrations and you get some gamma function, hypergeometric function, which encodes the pole of the bound states. So the pole of the bound states just come from an analytic aesthetics perspective, fully momentum space, just come from Fourier transform integration back in momentum space of a kernel. So it's an interesting, just from the aesthetics perspective, just to think about these things. This is this function with T over S, if you want, from the S-matrix bootstrap approach. Okay. So, okay, what's an example of the kernel? So, okay, as I said before, here you get like up to 2 p.m. So everyone here doing Amplitudes knows do this. I'm just going to explain, like you just basically sum up these diagrams. So you have a 3-level exchange, which is just the first Minkowski order. And the second Minkowski order is just given by this triangle diagrams in 4 dimensions. And you see that the massive propagator is cut. This is similar to the reason before, so you want classical physics, so there is going to be a delta function that linearizes the massive propagator, because you want to sum over, as I was saying before, the physical principle dictates that you should sum over all exchanges which are indistinguishable, classical. So these two things, if you work it out, is exactly this cut. So all the diagrams we compute for massive particle will have this cut on the massive particle for this reason, so it's a physical principle. And it's natural in the world line, but yeah, as I said, from amplitudes it arises in this way. So this for the conservative dynamics. One thing I want to mention here, you can make contact directly to conserved quantities, which is what you should do. As I said, because we want to go, we are now in partial wave basis, just from this asymmetric quantity theory perspective, you can make contact with the orbital momentum, which is just related to the total central mass momentum, like infinity, times the zero parameter that is x perp. And the kernel is a function of the rapidity, but rapidity is a function of the energy. So everything is essentially a function of the masses and the conserved charges, okay? So it's a function of the masses, the energy, and the orbital momentum. So now what you want to do, like when you solve the Coulomb problem, you want to go to energy from above 0 to below 0, right? So you want to do the same. So here was for energy above 0, this was for energy below 0. And now, because we have masses, you have just to subtract off the masses. So physically, you just subtract off the masses to something that is positive or negative. So yeah, the kind of idea is that you want to go from scattering orbit to bound orbit by decreasing this E, okay? And so you get this expression in hyperparametric space of the kernel or the iconal phase, and want to perform an analytic confirmation. So one key insight before doing this is that when you solve differential equations dynamically from an Hamiltonian, you can find a scattering model solution depending on the boundary conditions. Okay, so the differential equation is going to be the same. So if I write down Hamiltonian, I derive the equation of motion. I have the same equation of motion. I just change the boundary condition. So clearly, what I need is some control over the boundary condition. So everything is about the boundary condition, essentially, when you go to this bound state problem. And it's only because it's classical physics. So because it's classical physics, you write down differential equation in an ordinary sense. Okay. And indeed, like the interesting part is that this kernel is now proportional to the Hamiltonian. So if you're familiar with this, it's just classical mechanics. Essentially, you just have some convenient coordinate system in which your degrees of freedom are just described as some one radial variable. The reason why you can do this is that the motion is on the plane. So that's a particular type of configuration quadratic plane. I will go beyond this, but in the quadratic plane, it's going to be just related to the fact that the motion is on the plane. So you can just write this as a function of the radial momentum, the radial action, and this is what is called the amplitude action relation. In particular, see the contour of integration depend on the orbit. So in this case, it would be like from the point of the minimum turning point of the scattering, where they are very close to each other, to infinity. And we want to go to the bound case where we have like two turning points of this radial motion. So it is description.
So,
Any questions? Yeah.
that means that it will be singular in a zero centricity limit, the result. Right?
Well, it's also always meant to be an expansion of 1 over E. Yeah. It's always meant to be an expansion of 1 over eccentricity. Yes. Yeah. This is the way that you could connect the two things. You could try other things, but today I will discuss this method. But you could try, plugging something like really bound essentially and avoid these issues. You can, in principle. That's a bit harder. But this is a more like a gauge invariant type of approach of taking the charges and taking this function. But in principle, like quantum theory knows about bound states, right? So in principle, you can avoid completely talking about scattering and just talking about bound states.
Yeah, somehow it's the opposite limit of light.
The scattering thing, yes. For the bound thing, I was saying, like, it's just not developing good enough. Like, so you can always take the green function, take rescue the bound state balls. Nobody forbids you to do that, and then take the interaction.
No, but I mean, if I want something that is manageable as small eccentricity, what we need for light, then it's not trivial.
It's not trivial. Yeah, it's not trivial. I was just saying, in principle, quantum theory knows. So in principle, you can take residual green function on the bound state ball. It's just not here. You want to apply motion methods. So I want to apply some motion methods and trying to learn from motion methods, like what I can see, like, because they're very convenient for doing calculations. That's essentially the point. But yeah. So so here already in the figure I mentioned, kind of in Portugal, I will give more space to what they've done. So they've found this interesting dictionary, which relies really on changing this boundary condition the way I was saying. And the critical point here is that it is very interesting, and it's still like kind of subject to situation nowadays. Is there are two roots of the turning point for the bound motion. So there are an ellipse. So ellipse actually go from a distance from another. So there are two turning points in the motion. But the interesting part, they're both related to the same turning point in the scattering by a different analytic continuation. And this I find it very interesting. So you can analytically continue in this energy, and you can find the minimum turning point, like R minus is related to the the R minus in the bound case is related to the minimum distance turning point in the scattering, but also the R plus is related by a different analytic continuation. So this is the critical way of finding the relation, because if you didn't have this relation between the R plus and the R minimum, like you cannot do the boundary to bound. So that just doesn't work. The way to see this, you can think about this. You can think about potential, which is up to quartic orders. We solve by radicals. When you solve by radicals, you have plus minuses in front of the square roots, and it just turns out that if you flip the sign orbital angular momentum, you can flip one of the square roots. So you get exactly the square roots you need, exactly the root you need for doing this analytic continuation to work. So this is the way you could think about it. And one interesting thing that was not pointed out is that you could avoid the talking. So here it might be strange, like from outside perspective, say, oh, I just want to go below in energy, right? So I mean, like in the one-dimensional Coulomb problem, I want to go from energy above 0 to below 0. But here now it's two-dimensional problem, so there is energy and momentum. We will go to a 3D problem later, but now it's a two-dimensional problem. So you have to consider both the charges, so energy and momentum. It just turns out that it was found first that if you flip the value of the orbital angular momentum, you will find the analytic continuation you will need for finding the minimum, the R plus. And therefore you can rewrite the contour, because the radial momentum is invariant under the change in the orbital angular momentum. You can divide the contour in such a way that you can find this bound radial action directly from the scattering radial action. But you can also do in terms of the rapidity. So this is without changing the angular momentum. So you can also think only about energy. So if you think only about energy, you will have square roots in this rapidity, which always appear because they're related to basically the scattering. And what turns out to be the correct recipe is the summing of the average of the branch cuts. So you have two branch cuts because the square root, of course, define your Riemann sheet. So you will have two Riemann sheets, and you have two analytic continuation. You have to sum over that, and then you don't change over angular momentum, and this works as well. So there are different options. It's still unclear what will be the best, but I will focus on the first one at the moment. There will be other options. The interesting things, of course, generalized to a line spin particle, and this is very, very relevant, as we know that the waveform tablets at the moment are currently used for detection of basically line spin. So technically, if you can treat the case of a line spin, you can treat a large set of the data you need at the moment. But the motion is here still on the equatorial plane, so you might want like to do some precession, right? So, and now that's the main point of this talk, like talk about precession. So I will talk about the case in which the orbital is a subcase of the full general case in which the orbital angular momentum and the spin of the Kerr black hole are not aligned, and so there is precession. And so now you see before it was a two-dimensional problem with ENJ, now we go to 3D. So it's energy angular or azimuthal angular momentum, as we'll see at Carter constant. Any question at this point before I move on? Okay. Well, all right. So we want to consider then generic orbits for Kerr black hole. In the case, as I said, they're not aligned, so that the motion does not stay in the plane. Okay. And this is described, this is quite simple, and people have understood it since long time ago, basically Carter, 1968, but it's described by this geodesic Hamiltonian, which is, it has some convenient variable, and I will discuss more about this convenient variable later, but these are the Boyer-Lindquist coordinates. And the interesting point is that Carter discovered that basically the Kerr problem is integrable. The geodesic motion on Kerr is integrable because you have enough conserved charges to completely solve the motion. And now what happens is that the action I was describing before is not only the radial action, but there is a polar action. So now and this will be crucial for precession because now we have some extra degrees of freedom in another direction. And this has been already found by Carter, so we just basically are borrowing here the idea and connecting it to amplitudes. All right. So here there is kind of GR type of perspective. So for people for GR will like it more. This radial action is related to some radial potential, and the polar action is related to polar potential. This thing's decoupled because it's a particular Hamiltonian equation for Kerr, as I said. It's the separability of equations. And these are all functions of these conserved charges. So the mass, the energy, the azimuthal angular momentum, and the Carter constant. And in particular, the Carter constant is a measure of the motion of the equatorial plane. So if you define some 3D orbital angular momentum, this is not conserved. And in particular, this is related to some modification of the equatorial projection of angular momentum, essentially, which is not, that the equatorial projection is not conserved because there is a spin part, but the Q is conserved. So there is a combination of those. So now you can try to play the same game. So you want to now understand like this relation between scattering bound orbits, like with precession. Here, the roots are depending on another variable, which is essentially what I was saying, like it's related to the equatorial projection angular momentum. And it's this LQ defined by the square root of Q plus the L square. And okay, so we want now to find the relation between the roots in the bound case and in the unbound case, okay, make the connection. And what we found is that this works essentially if you flip the value of LQ. So this, like in the B2B dictionary that has been developed so far, you always have some odd and even parity of some variables, so just to flip. And in this case, like the natural thing to do is to flip this LQ, which is related to, as I said, the equatorial projection, the angular momentum in some sense. And so we found this relation between the roots. Kerr has a quartic potential, so you can actually solve by radicals and see explicitly the flipping sign. And then which implies this relation for the radial action. So this maybe was expected, which you could find some extension. But the point is now that we have the polar action. The polar action is a completely different story. And okay, I will come back to that later. I will just show how the radial action works first. So what we do, we just so usually people solve these integrals in terms of elliptic functions, but that's not convenient for the PMS function, it turns out, so we're just going to solve them in terms of pergeometric. So that's the reason. If you're familiar with the elliptic solution of the curve problem, we're doing a pergeometric just because the PMS function works better, essentially. At least that's what we found. And this is a nature express. So if you express the radial potential in terms of the 1/r, you can easily find the solution in terms of the roots. And you get an all-order expression. It's infrared divergent, as it should be. So these things have to be regulated. There is a long distance IR divergence. But this drops off from all physical quantities, right? So in particular, divergence is not proportional to the angular momentum, so probably scattering angle will be independent of that, and other physical observables will just be independent of that if you consider something physical, okay? As I will discuss more.
Because like phase or stuff.
Yeah, for example, like time delay. So time delay requires to consider the time delay for one null geodesic compared to another null geodesic. So you always need to compare the two things. And that's when you subtract off this infrared divergence epsilon. Otherwise, it doesn't make sense. This is like, you know, amplitudes are not observables. You can construct observables from amplitudes, but they're not. The amplitudes are infrared divergence, and this is also manifestly showing here. So that's what we're showing here. Okay. Well, they fully transfer this case, but okay. Okay, so what's the most general corruption? This was found by Alex Pasca, Kapek. There's also a paper with Brada and geodesics. But the interesting is basically just the composition what you expect from a contour. So if you have your polar potential as essentially two polar turning points, and you will just have oscillation all around the two turning points, and then you will have one piece with depend on the final initial angle, which you start with some angle, so a polar angle, and you end with some other angle. And so there is a number of turning points, and there are the roots of the polar potential, and there are some signs depending on the incoming outgoing configurations. Right. Yeah. So for what is of interest, like of the amplitude community, basically you can just PM expand the equations and see that the number of turning points in the polar motion, just like in the radial motion, is 1 for the scattering case and 2 for the bound case. So we found that this by really expanding the equation, and they're just you find exact numbers. Which might be a surprise, maybe it's not, but it should be something straightforward to see from the amplitude, but it's a bit difficult to work this basis. So yeah, but it's interesting that they are fixed completely. So I just didn't put this number, I derived this number, this one, this n greater or equal 1 and n less equal 2. So these are completely fixed. And the physical picture is that in this case, we have started for simplicity on the equatorial plane, but then you go off the equatorial plane because Q is different from 0. So the Carter constant is different from 0. So it will just go, the polar motion will just go up and down, will complete one cycle in the bound case. So it will be 2 polar turning points, but half cycle in the scattering case. So it will be only one polar turning point. Okay. So here the point is that how does this connect, you know, and now we have a relation between the contour for the polar for this polar action. So we now have the full map. And okay, you can write down lower the action. As I said, you can use elliptic function, but that's not easy to expand. So we found it easily just write in terms of hypergeometry. We just get the PMS function at all orders if everyone needs at some point. And we found this analytic continuation of the polar action. So this is an analytic continuation which allows you to derive perception effects for the simplest case possible, which is a Kerr black hole with a massive probe particle. But it's all orders, okay, in perturbation theory. So it's a multiple orders perturbation theory for these actions. And now it's time to have fun and computing some scattering bound observables. So once you have these actions, everything is just ready to differentiation in some kind of form. So we discuss both scattering and bound, just give a survey of what kind of observables I'm talking about. So the first one is the azimuthal scattering angle, which is just a derivative. So it's a conjugate variable to the orbital momentum. So just derive the orbital momentum. Here you have both radial and polar pieces. So you will just recover the standard expansion. And one thing here is, of course, we have this LQ. So we now have like some dependence of this of the Carter constant, like in the expansion. And yeah, and so this matches the result, for example, by adjusting. But yeah, the general expansion I think is new for generic orbits that is written in this way. It might be written in other forms, but this is kind of nice from the post-Minkowski perspective to also check some type of precession effects. All right. You can also derive the Born deflection angle. So this is one may ask, why you don't consider one single angle, because you have one Kerr black hole at the origin. So I have a particle. I can just take, a dot product. For example, I can define some dot product of P in dot P out, and that's one angle. Okay, so that's not two angles. But it turns out that if you want to connect, as I'll discuss, like to the bound case, the bound case really cares about this separability in these equations. So because you want to go to, at some point, action angle variables to define frequency ratios, as I will describe, you might want to actually decompose things into an axis and just do the calculation this way. But in principle, you can also derive one single angle from amplitudes. So this is all, of course, equivalent, like the two pictures are equivalent. Anyway, you can compute that. That's proportional to the Carter constant. So if I set the Carter constant to 0, that's obviously vanishing because that's a equatorial plane. And that's because it's in the denominator of the delta theta. Yeah, and then you can do some geometric transformation. So if you send the spin to 0, there is no precession, but the plane is still inclined. So that means that there is a relation between the two angles, right? So if you have, if you send the spin to 0, there will be a plane of the motion essentially, but that's not compared to the coordinate system. Is not on the equatorial plane. So you will have some projection, and so that's what this relation is about. We check that is consistent with the geometric perspective. So you can check by a change of coordinates, essentially. Yeah, sorry. Yeah.
So you had a formula for delta phi.
Yeah.
In terms of derivatives of the actions.
Yeah.
What about delta theta?
Yeah, it's only derived from the equation of motion. Yeah. From the equation of motion. Yeah. It's the relation. I think that's something like this. This is equal to the integral d theta. I guess you have seen this expression before. Yeah. And then this is a theta out. You expand this and you solve it. That's an elliptic function. You expand it. There is no, yeah. We look at your paper and the previous paper. You also cite on the type of trying to get conjugate variables for different angles. So yeah, unfortunately, that's the way we proceed. But yeah. It would be awesome to have a better way of having a 3D covariant description of angles. I agree. That's not yet the case, but we do it again. So yeah. All right. Yeah, you can also do time delay. So this is an example in which the infrared divergence has to cancel. So it doesn't make sense to compute just derivative over energy in the scattering case because that's infrared divergent. That's depending on the epsilon that I was introducing as a regulator. So what you have to do is compare a geodesic with respect to another non-geodesic and further distance. And so you compare only time delay of a geodesic compared to another. That makes physical sense, and the infrared divergence cancel off, and you get a finite answer, which matches expectation from some of the people, so here Fabian, for example, in the equatorial limit. Again, that's all generalized to this Q dependence. So the Carter constant is it's a new formula in itself, but yeah, it reproduced no results. Right. Okay, so something interesting yeah, so I was saying about this fact that we have two angles instead of one. And when you go to the bound case, you compute observables. What is an observable, right? So observables are fundamental frequencies of the motion. So these are defined with action angle variables. And so you cannot get around that. You want to have frequencies, you want action angle variables. Because otherwise it doesn't, you don't define something coordinate independent. You want something coordinate independent, so it must be geometric. A geometric thing is an action angle variable. So that's what is done here. So with this coordinate, with this representation, you can always define action angle variables. And yeah, so you can define the three frequencies. That's been done by a nice paper by Smith in 2002, celestial mechanics in Kerr black holes. One thing that I want to emphasize, you still have dependence on the choice of time coordinate when you define a frequency. So because this matrix is time independent, you do expect to get that what would make sense is a ratio of frequencies, because you don't want time dependence. You don't want to be dependent on the choice of a particular time. So these frequencies are depending on a choice of a particular time. So it would make more sense to compute frequency ratio. Turns out when you do the PM function, it doesn't make sense only for frequency ratio. So it's consistent with the expectation. And this corresponds to the pre-astron advance and the precession in the orbital plane, which is the precession I was talking about. And so you just compute, you match, it matches no results in the equatorial limit again, so that's more general. And we also have the precession of the orbital plane. So this is, yeah, it has been written in some PM way with other people, but in a very complicated way. This is a clean PM function like these things, okay? So, and as expected, the frequencies have to become degenerate because there is only, you know, when you have a circular motion, all the frequencies are degenerate. Now you have the equatorial plane, if you send it to 0, 2 frequencies are degenerate. So it makes sense these things collapse into each other, the frequency ratio, as soon as you send A to 0. So that's some of the physics. Any questions before? Well, okay. Right, so I just want to flash some results. These are based on things that have been going on in the literature for some time, but we're just trying to clean up what I can. You know, we have talked about conservative physics, but now we want to do radiation. So the interesting things about radiation, we know that the current problem in B2B is this no local in time effects. So at the end, there's going to be something. We need to go to radiation to consider the full problem and try to understand the full problem for density continuation. So you can run a similar recursion. This is basically just dressing up the previous recursion. It's possible to show that this is the correct thing to do, like the level of string Dyson equation, take on shell reduction, and you just end up with this recursion relation gives you the 5-point amplitude for one emission, one graviton in terms of a relative kernel and some iteration with a 4-point amplitude and the previous kernel of the 4-point iteration. I will restrict to positive energy, so there is a subtlety for static energy, which I'm not going to talk about, but you can ask me offline if you're interested. So you can apply the same symmetrization procedure. And what you get is that, and this is still in terms of this, you know, two massive particle reducible diagrams. So what you get is the 5-point amplitude. It's related to this iteration of the classical kernel discussed earlier, and the 5-point amplitude with one less two-particle reducible diagram, and the 4-point and the relative kernel. So there is an interesting recursion, and a similar thing holds for emission and gravitons. It's quite straightforward, and can we find the solution to the resonation? And yeah, it was expected that we can do, since it's known that you can do the radiation part, but I'll just clean that up, like from this video point of view. So what you can do here is write this as a convolution again. That's a kernel. So it's a 4-point kernel times the 5-point amplitude with n of these two-particle reducible diagrams. Relative kernel and the 4-point with n two-particle reducible diagrams. You go to new parameter space, but now you have two momentum transfer. So that's a generalization of the previous feature, so that there are this momentum Lagrange initial pair of a finite pair of the massive particle, which is linked together by the radiation. So it's a delta function Q1 plus Q2 minus K. So, and once you apply this Fourier transform, then, not surprisingly, you get a result, which, as I said, like I was also participating today, like 2 years ago, like we got this result for the classical matrix, which is an aconal phase and coherent state of gravitons, which represent the classical wave. Now, remember that the classical kernel, the 4-point, we just linked to the amplitude relation. So now, you know, basically, this calls for some kind of finite continuation of relative kernel. And one nice picture here. So yeah, I'm going to daily talk for the waveform, so I will not talk about that.
I'm probably going to talk about something else. So
that's fine. Yeah, okay. That's so annoying. Okay, fair enough. But anyway, it's the endpoint amplitude like can be nicely written in terms of this exponential, the 4-point function, 4-point classical kernel, and some 5-point amplitude. So there is some, in particular, this is an endpoint amplitude on the left. So basically, by expanding this exponential, you're going to recover the endpoint amplitude. This, I would say, it's now understood for positive energy. So this kind of proof for positive energy emissions. The issue is static effects. So static effects are more subtle, and as I said, that is discussed offline. But for positive energy, this is an exact solution. So it just comes from string relation. So once you do this symmetrization procedure, you apply the Fourier transform in the way that I described, like you just get exact results. Some comments. This unifies potential relative modes. So I think it's nice because in some sense, like you don't have to treat things separately. That's a unique S matrix that has together like the two pieces, and you don't just have to combine different information from potential relative modes. And also the observables have to be derived only by this representation. It's a gauge bar representation. So there should be some nice amplitude action relation like for general things. And one, so that I'm still kind of trying to understand. One interesting point is, can you understand relative information the way that's a possible thing to do. Yeah, so I'll close it up. So we derived the classical this Liddell equation for gravitational bound system for particles with and without spin, and with this physical principle of basically symmetrization over exchanging of internal gravitons and external gravitons. We solve it in parameter space, and we relate it in a conservative case to the Jacobi action. We discuss the generalization of the B2B for generic moment orientations, where there is this precession effect, which so includes both radial and polar action. So in particular, the polar action was never discussed in this contest, and we focus on massive particle and curve backgrounds. We provide some more expression for service probe limit, which can be useful to make contact with the PM's function and also with the GR literature. And future related directions, I think, understand this amplitude acceleration for general sphere orientation, but also Justin was asking the 3D dynamics, having full covariant understanding of that. So in what I've said, there was no orbital elements. I never talked about orbital elements, some gauge dependent quantities. It's all gauge invariant. So it's all dependent on charges, and that's kind of a clean setup like for do this. There is this interesting generalized Carter constant for spinning particles. So what I said, they might say, oh, well, you consider just scalar in care, but we know that I think up to the quadruple order, there is some conserved generalized Carter constant, which Justin has work on. And we would like to understand the intuition relative observables, eventually trying to bypass this problem in detail, in the non-local piece in the tail, and also some self-force. I mean, I was talking about geodesic. The geodesic is the next piece that you plug in when you do the 1SF calculation. So technically, it's very relevant to understand also geodesics as a kind of proxy to put into the equation for the 1SF. And yeah, thank you.
Any other question?
Say a little bit more about the static.
Okay. So if you, I can say a bit more. If you, so the in general, as you know, like 3-point amplitude, like with one mass and emission graviton are considered to be zero in Lorentz signature, but technically they are supported on zero energy gravitons. Okay, so this is particular proportional to some delta of omega. Technically, so it vanishes for all positive energy, but it doesn't, and this enters into calculation of linear memory and angular momentum with static effects. For example, like when you compute the angular momentum at 2 p.m., you get contribution of this type. You get contribution of this type, which comes, so you have factor of kappa here, so it's order G squared. So that's the angular momentum emitted in the scattering finely. And it has contribution from this 3 points supported on zero energy. So that's integrated in the phase space for the angular momentum expectation value. And so this is kind of related to this BMS ambiguity. And in particular, if you do write the recursion like that, I didn't have contribution of this type, which actually are there. So contribution of this type when you attach the leg to one of this external leg. So you can have contribution like that are.
If you set aside those contributions, then everything
is gone, is exponentiating, yeah. So it's only for static effects, but they might be relevant for the angular momentum and other things. And so this makes it a bit subtle, like. But except for that exponentiation work, it just
the question is it going to be an obstruction to continuation from positive to negative energy?
Yeah, that's I don't think that actually these are posing problems in general.
I mean, it seems to me this should be a red herring as far as balanced state physics is concerned, but I mean, some subtlety.
I'm not sure because actually, I mean, well, I have to look into these things, but I've seen these diagrams. So okay, I've seen similar diagrams in a kind of calculation for bound states in a different framework, like in dark matter physics. So some people do cross section for production of some matter under matter particle bound state to dark matter, and they have diagrams like this, which are only supported on one leg. I guess your point is right confirmation of those things, but I don't know. Okay, yeah, it's a good question. I don't know. I know that people have treated that like in some context in state physics. So yeah, they're very subtle because there are a lot of terms. If you just include all the touching, all the gravity next to all the possible terms, it's a lot of terms. You can group them up, but it's just yeah, there might be subtleties. So yeah, I hope there are not.
Let me ask one.
Oh yeah.
For internal lines, you always use Feynman operators.
So, well, this is for them S metrics. So luckily, when you do calculation of observables, like for example, the KMC instruct us, you have to add some unitary cut contribution. So I mean, you don't own the S matrix. The S matrix is a proxy to the observable. And so the problem of the causality and the in comes when you compute the actual observable. So that one, will be like some incoming state, the S matrix, and then your operator, and then S matrix. And so when this in particular includes not only effects, so this is your final operator, so it could be angular momentum, and includes the S matrix and the conjugate variable in the formalism. So what I'm saying holds for the final operator, like in the standard S matrix picture, then you combine with the conjugate S matrix, and that would be observable. So I said that this problem talking about conservative contribution, like in the Amplitude copy, but in general, they will enter in the calculations, like at higher orders, there will be this epsilon problem, and you have
you should follow the rules.
we follow the rules. Yeah. I mean I mean it's just that it's not. Yeah, it's more. You have to use schemes in this way, like or some kind of framework. Okay, that's what I'm saying. You have to use some meaning framework. So yeah. So this would be the right answer, despite this being just as simple. So it doesn't matter this which.
No more questions?
So about the analytic continuation for protein physics.
Yeah.
Maybe I'm misremembering, but you showed us how it works for the actions.
Yeah.
What about say, for the angles?
Yeah. So I don't have that in a clean way yet. Yeah. I have the one for the action. So
I assume you check.
I checked. Yeah.
That it's not. So you're saying it's not just. So for example, delta phi is you flip the sign of all the angular momenta, and then it gives you.
No, I think there was a, so, yeah, there is this term that is polluting the calculation. It's not just, So this is the standard term, I think, and this is the extra term.
Yes.
So this extra term is the. So I got some problem in matching this with the derivative of the I theta over L in the other formula for the azimuthal angle. I don't know how that is resolved. Yeah. I matched results with what is available in the literature. But,
So,
yeah.
so you framed everything here in terms of the frequency.
Yeah.
I guess, so there's still like an angle.
There's probably other way of seeing that. Yeah, I'm not disputing that.
You know, without the spin, the scattering angle continues to the periastral defense.
That's right, yeah.
So, at least for phi.
I do expect that there is something similar, yeah.
Analog of that.
Yeah.
Equal precision.
Yeah. So yeah, we found some obstruction in related to this guy. We did the J theta over DL, which comes from the normal formula. So if you go back, there is a di theta over dl, and then dir over dl. So now if you go, so if you use this equation, which is consistent with Smith, you get an extra piece. So then I got some problems understanding that extra piece. So that's the reason. Of course, in the equatorial limit, everything works. And there might be better alternative techniques. This Milno time that Martin suggested, maybe solve the problem. I don't know. If you look at the formula, they're different. There is this prefactor, and this is correct, and which is checking the same as Smith, and it gives you the right form. But yeah, there is this something. Yeah. So that's the reason that we don't find the Giannis continuation in that one. But it works the level of the actions, and for the moment it's okay. Of course, one would like to improve. In any case, you want to go full misaligned case and trying to understand that as well. Like, and maybe that, yeah. Also talking about these frequencies is only very much related to the actioning variables existing in care. And you want something more general, like, but yeah, it's still to be understood.
Then we can stop here for the talks. Thank you again, Riccardo.
Sorry?
Tomorrow at 9, right?
Yes, tomorrow afternoon, then if you don't have student talks.
So you haven't managed to twist anyone's arm.
No, I'm not a violent person.